So now I'd like to cover the mass moment of inertia. This is a property of an object, just like there's a lot of other properties of objects. The mass moment of inertia, and they have a symbol for it, cap I. It's the same symbol as the area moment of inertia, isn't it? But here, maybe you want to do it around the x-axis. It would be the distance from the x-axis. That would be measured perpendicular distance. That would be in the y direction, dm. So the distance from the x-axis squared integrated over the object's mass. Now, we're not going to get too complex. What we're going to do is we're going to have rho is equal to a constant, unless there's a particular one or maybe two problems in the whole chapter that deals with non-uniform density. But we're uniform density. And this topic is built on when you get to the dynamics class, engineering statics followed by engineering dynamics. So there they may be a little more complex, but I doubt it, in having a variable mass density. How is this mass moment of inertia used? Well, it's used in characterizing the rotational acceleration of an object. And so there's two equations. I'd like to, one you're very familiar with, F equals ma. And what is that equation used to describe? Linear acceleration. And in this equation, what exactly is F? It's the force. What are the typical SI units for force? Newton. And M, it's the mass. Typical SI unit for mass? Kilogram. And A is that linear acceleration. And what are the typical SI units for acceleration? Meters per second squared. And now you have over here another system of equations. Just like for linear acceleration, you have angular. And I know everybody in the physics class that you took, which is a prereq to this class, were exposed to angular acceleration. And so the basic equation is just like F equal ma. It's m equal I alpha. Maybe you have different notation for it. But what is the cap m in this equation? It's not just the force like F is. It's the moment of the force. Or if you have multiple, you have the sum, or sum of forces, sum of moments acting on an object. And then what is this I? Well, that's the focus of the study right here. It's the mass moment of inertia. It's the mass moment of inertia. And then what is this alpha? It's the angular acceleration. Okay, let's take a look at the parallel. So you have two accelerations, linear acceleration, angular acceleration. Use A or alpha. That's parallel. F or m, you have the force, or the moment of the force, and then you have m for mass, and then you have cap I, mass moment of inertia. Hopefully you see the parallelism. What is the units, typical SI units for the moment of a force? What is that? Newton times? Meter. All right, now let's leave off the mass moment of inertia, or you can just look at the equation. It's the integral y squared dm. What do you think the typical SI units for mass moment of inertia are? Kilogram meter squared, right? Kilogram meter squared. And then angular acceleration, well, what is 1 over second squared radian? We leave off as dimensionless. So as a quick review, to help tie these concepts together, I think the more often you see these concepts and they're laid out, you see the parallelisms, you can remember them. But you had x for position in maybe meters. Then you had v. What was v? dx dt. V is velocity in units of meters per second. And then a, that's dv dt. That's acceleration, linear acceleration, meters per second squared. What about in a rotational system? Well, we have theta. What is that? The angular position. Just like in a linear system, you have a coordinate system. You say, where's my object? You say, well, it's at this location. What is that location? Well, measure from the origin. It's maybe, 2. X is equal to 2 at that instant in time where that object is. Well, in a rotational system, you have a coordinate system. Let me just draw it. Coordinate system. And then you could have something that's going to be rotating, and you say, well, at this instant, what is its angle? Theta. And so it can change with time. So what is omega? That's the time derivative of the angular position. That's an angular velocity. And then what's alpha? Alpha is the time derivative of omega. So that's the angular acceleration. All right. Angular position, SI unit for angular position would be radian, which is dimensionless. So you could either say radian or dimensionless, either way. And then angular velocity, it would be 1/2, or you could say radian per second. And then for angular acceleration, 1/2 squared, or you could say radian per second squared, because radian is, again, dimensionless. So hopefully you see that parallelism. If what happens if I have a large a large mass, m? If I have a large mass and I want to accelerate it, what do I have to apply to it in order to accelerate it? A very large force. And so mass is a measure of its resistance to its change in the current state of motion, right? If it's at rest, it's going to have a large force to get it to accelerate. If it's already moving like a freight train, don't pull out in front of it. It's just going to roll right over top of you, okay? Because its current has such a large mass. Well, the same thing here. If you have a large mass moment of inertia, it takes a large angular moment of a force to get it to spin up, to get it to start to really accelerate. So anyway, here are the equations for I. You can have it around a particular axis, or a lot of times it's around a particular point in 2D, and that axis is coming out of the paper. All right? So maybe you write it like that. Here, what do they have? R, it's that distance from that point coming where the axis is going perpendicular to the paper. That's R squared dm. Or here is the distance from the axis in 2D. So linear motion, angular motion. All of these hopefully have been a good review for you. So it's the mass moment of inertia is an object's resistance to change in its state of angular motion, whether or not it's going to accelerate or decelerate. All right, so these are the equations for I. Both of these, they're just cousins. Okay, we are going to study, just like we did for centroids, how to calculate it for a uniform body, for an object. Well, we want to get good at applying the calculus that we invested so much time in learning, and we want to be able to integrate to calculate that mass moment of inertia. Again, for uniform bodies with rho is equal to a constant, we're not going to be doing anything too tricky. Then we have for composite bodies, just like we did for centroids. We'll be able to sum it up for a system made that's a composite body. And when you do the summation, often you have to transfer to a common axis of interest. So we're going to have a review of the parallel axis theorem. Here it's written for the mass moment of inertia. If somebody said change one letter in this equation, and it would be the parallel axis theorem for the area moments, which term in this equation would you change, and what would you change it from and to? Change the m to an a. That's it. It's really pretty easy, isn't it? So if that was an a, then you'd say, oh, there's the parallel axis theorem for area moments. area moment of inertia. And then here you have it for the mass moment of inertia. All right, what are the typical SI units for the mass moment of inertia? First clicker question. So the equation was the integral I, that's what the term is, that's our symbol for the mass moment of inertia, is equal to some distance squared. You could put it r squared dm. So what you're going to pick up is you're going to pick up a meter squared from the distance squared, and dm, that's a little chunk of mass, a kilogram, times meter squared. Isn't it C? So there it is, C. All right. When is the mass moment of inertia of a body less than 0, i.e., when is it negative? When the mass is negative? When the distance from the axis of revolution is negative? Or never? All right, let's see where we're at on that. Okay, let's do this. If I do the integral of r squared dm, how many systems have negative mass that you know of? I mean, I can say it, but it doesn't make any sense. I mean, I'm not an astrophysicist with black holes or other things. We're pretty much Newtonian engineers. I know that sometimes we deal with nuclear, what happens in the nucleus when we're fissioning or fusion. We understand that, huge release of heat and that, but negative mass makes no sense for an object. Now we can use that when we have composite systems, but that's a mathematical trick to count for holes in our composite system and get the right answer. So this is always positive. All right, what happens if r is negative 2 meters, and I square it? Can I get anything r squared ever be negative? I mean, I'm not an electrical engineer and I have I. Remember I, square root of -1? I mean, you saw it maybe in your physics class. Guess what? You're a mechanical, civil, goodbye I. You know, we just don't see much of it maybe in your controls. Okay? So this is the integral r squared dm is positive. You won't have a negative. All right? All right. All right. For the slender rod, here's a depiction of the slender rod. Can you see what axis the rod is aligned with? What axis is that? The x-axis, true? So we had this slender rod. I didn't give a mass to it. Maybe I say the mass is 1/10 of a kilogram. So there you go. It's 1/10 of a kilogram for that slender rod. And we don't know how long it is. It's a couple centimeters long, but that's not relevant. Let's look at the question. For the slender rod, the mass moment of inertia is I sub x is less than -1, just looking at the magnitude, don't worry about the units, is equal to 0, or I sub x is greater than 1. And again, just look at the magnitude of it. Don't look at the units. All right. So if I think back to it, it's our inertia. It's mass moment of inertia. It's the sluggishness at which for accelerating in the angular. So if I say I sub x, each one of these have x, right? It's the integral of, if I looked at it, maybe the y, z plane, it would be around this point, which is the origin, and the equation that would make sense is r squared dm. What is r? Well, it's this distance r from the origin. So what you're thinking is how hard or sluggish is it to spin that long, slender rod around the x-axis? That's the property that we're dealing with, this mass moment of inertia. Well, you need mass pretty far away. A lot of mass far away makes for a large mass moment of inertia. Mass that's right close to the origin and you're trying to spin it up around the origin, guess what? Doesn't take anything. if it's all at a dot, centrally located, so it's close to zero. It can have a very small mass moment of inertia, and this would be a case of one, where it's very small. Why did, greater than 1, it's, I didn't put the units in there, but you could play with the different units of kilogram, meter squared, gram, centimeters squared. Without the units, 1 is, I got to figure out what that means in the particular units. So this was a tempting answer, but the best answer was B. That's what I was looking for. All right. Thank you for nobody selecting A, right? Okay, here's another question. For that slender rod, what is the mass moment of inertia? There's 3 equations. Which one is true? Is Ix equal to Iy, Ix equal to Iz, or Iy equal to Iz? Okay, so basically if you're looking at Iy, it's how it spins in the xz plane, right? Or if you're looking at Iz, it's how it would spin or have resistance to spin or inertia with respect to spinning in the xy plane. And so what's the same? The yz, isn't it? So let's go ahead and look. And we had quite a few correct. That's very good. Well, hopefully we have a good feel for what this property is that we're calculating and how it's used in dynamics the next class. Now let's go ahead and do the math. Determine the mass moment of inertia, I sub y, of that slender rod. Well, we're going to talk about it in terms of the mass of the rod, even though it's not shown. There's going to be some mass of the rod. And if I wanted to calculate I sub y, I could think about the integral of r squared dm, or just integral of diy. Just sum up the little chunks of the mass moment of inertia for different chunks. Different chunks, all right? Well, it looks like a chunk right here is located a distance from the y-axis. That distance is x, isn't it? Isn't that distance x? And so you could continue to work on this. You could say, okay, it's x squared times the dm, integral x squared dm. All right. What is the chunk of mass? That you could think of it as a rho times a cross-sectional area. I know that's very slender, so it has a small cross-sectional area, times dx. What is the cross-sectional area times dx? Doesn't that give me a little dv? Rho dv is a dm? Am I moving too fast? Rho dv is a dm? That all makes sense? All right, so I can replace the dm by rho cross-sectional area dx. I'm going to integrate from 0 to L. That's it. I start 0 and go to L. All right. The rho cross-sectional area comes out. I'm left with 1/3 x cubed evaluated 0 to L. Rho cross-sectional area 1/3 L cubed. All right. If I take one of those L's and I say, okay, 1/3 L squared times rho A sub C L, what is that equal to? My mass. So I sub y is 1/3 m L squared. Can you see what I sub z would be? Same thing, isn't it? 1/3 m L squared. How about if somebody says, not this y-axis, put it through this y-axis, going through not the beginning of the rod, but the end of the rod. Guess what? 1/3 L squared M. So there you go, 1/3 mL squared. Well, what do you do now? No, put it through the center of the rod, through the center of mass of that rod, through the centroid, okay? Again, rho is constant through this rod, and the cross-sectional area of the rod is not changing either. I sub y is equal to the integral, and then we're going to have that x squared, the distance, thinking about going out to this chunk right there, x, times rho a sub c dx. But now we're not going to go 0 to L, so that the integration is set up the same, but what do we do with respect to x? Don't we go from negative L over 2 to positive L over 2? Yeah. And so we're left with rho a sub c 1/3. Then we're going to have x cubed evaluated plus L over 2 minus L over 2. So we're going to pick up rho AC 1/3 L over 2 cubed minus a negative L over 2 cubed. So you get L over 8 minus L over 8, but it's a minus, so it's a plus. So you have 1/8 plus 1/8 L cubed 1/3. And so what do we pick up? That's 2A's, that's 1/4, so it's 1/12. Then you're going to pick up L squared M. I sub y. 1/12. If you remember, that's very similar to what we did with the rectangle, isn't it? Yeah. Yeah. With that area moments. All right, determine the mass moment of inertia, I sub x, of the circular disk of thickness dx. So this is our x-axis, and we have a little disk of thickness dx, and we want to calculate that I sub x. Okay, so what is that I sub x? Equal to the integral of some distance. Here, you're going to have, I'm trying to draw it. So what we have is we have this r squared dm, and so we don't set it up. We set it up as little rings. That's how we set it up. It's not little. Try that. How's that? That goes all the way around. And so this thickness of the ring is dr. And what is the circumference of that ring? 2 pi r, where r is the distance from the center all the way out to that current location of the ring. 2 pi, isn't that the circumference, 2 pi r? All right, so if I take the circumference multiplied by the thickness dr, that gives me an area, and then I push it a dx, that gives me my volume. Isn't this dv? You've done enough integration, hopefully, in this type of coordinate system to see that. And so if I multiply, so dm, the little chunk of mass, is rho dv. All right, so let's replace. This is equal to the integral of r squared, rho 2 pi r dr dx. Okay. We are going to integrate with respect to either x or r. Let's do a clicker question. I want to now integrate. This is integral right here. I'm going to worry about my limits of integration. Do I integrate with respect to x or integrate with respect to r? All right, well, I'm not trying to be tricky. I'm just trying to, we're going to integrate with respect to r, and our r is going to go from the center, 0, out to cap r. And we're leaving dx alone. There's no, it's a constant thickness that's just called dx. So that's what I was looking for. So the rho comes out, the 2 pi comes out. we're left with r cubed. You can even pull the dx out. And then we have the integral of r cubed, which is 1/4 r to the 4, evaluated 0 to cap r. So what do we pick up? We pick up the rho. You're going to cancel, you get a pi over 2. You'll get the dx. And now you'll pick up cap r to the 4th. Well, what is the entire area of that whole disk? Pi r squared. If I said, what's the volume of the disk? A times dx, which is pi r squared dx. And if I said, what's the mass of the disk? Rho times v, which is pi cap r squared. Well, put a rho in there. Rho pi r squared dx. So I say, okay, there's our pi, pick out r squared with the rho, and so you pick up 1/2 the mass times the r squared. That mass, maybe I should have done it in 2 steps. Okay, let's do it in 2 steps. Rho pi r squared dx 1/2 r squared. There you go. So that's equal to the mass 1/2 m r squared. Makes sense? Or you could leave it as 1/2 rho area of the entire disk dx, just like I left it up there, times 1/2. Well, 1/2 is already there. Put the r squared. You could leave it like that too. Once we have it for a disk, we can use it for a section that can be made up of a bunch of disks, but probably the disk won't be the same radius. They'll be changing radius. Well, that makes it a cone. So determine the mass moment of inertia I sub x of the right circular cone. So this is our cone. This axis x goes through the middle of that cone out. So the cone has length h. At the base it has cap r. And the line that describes the y as a function of x is cap r divided by h times x. Hopefully that equation makes sense. So how do I calculate this I sub x? Well, let's sum over all the little dix's. And what we just gleaned from the previous problem is for any generic disk, right? And so what is that? I'm trying to show a disk right in there of dx. What it would be that mass moment of inertia of that disk? Wasn't it 1/2 cap r squared? But here we have to be careful. In the previous equation, cap r was that current radius of our disk. And so what we have is we have this current radius is y. That's what it is, isn't it? Y. So it'll be y squared times the dm, the mass, which is the rho, times the area, which is pi y squared, times dx. And we're going to integrate over the entire length in the x direction, which goes from 0 to h. That doesn't look like a great h. H. All right, so let me do the 1/2. Now for the y, we substitute, well, first of all, let me play with it. Y to the 4th dx. But y is equal to a function of x. So we're going to pick up the r divided by h to the 4th. We'll pick up x to the 4th dx, pi rho 1/2. and we integrate from 0 to h, integrate 0 to h. So we pick up the 1/2, the rho, the pi, r to the 4th over h to the 4th, 1/5. Then you have x to the 5th, evaluated 0 to not cap h, 0 to lowercase h, true? And so that's going to be 1/2 times 1/5 times the rho, pi, cap r to the 4 divided by h to the 4. We pick up h to the 5th. And so a lot of those h's go. What is the volume of the cone? I have pi, the base radius of that cone squared divided by 3h is the volume of the cone. So we pull that out so that we can get rho times the volume of the cone. And you pick up that it's equal to, this is a bad looking 3, isn't it? 3. So I'll have to put 3 divided by 10 rho pi r squared over 3 h r squared. This is the mass of the cone. And so I sub x is 3/10 the mass r squared. 3/10 m r squared. Let's continue on. Well, before we get to composites, we want to cover the parallel axis theorem. So what is the parallel axis theorem? It's going to be the mass moment of inertia at a different axis is equal to the mass moment of inertia going through the centroidal axis, and that's parallel to that axis of interest, plus that distance squared, perpendicular distance between the two axes times the m. So how did we set it up and do it for the areas? Well, we had a little 2D problem, and we had our global x and our global y, and we had the centroid of that area, and we had a centroidal x and a centroidal y. And what we did was we said, well, I'm interested in doing this integral of, I'm going to do it for a particular axis. Let's do it for the x-axis, I sub x. That's the integral of y squared dm, mass per unit area times dA. It's like a area density instead of volume density. Mass per unit area times dA will give us that dm. All right, then y squared. Well, we're not having a different density as it changes location, so that's constant. That can come outside that integral. And so basically it boils down to y squared dA. Hey, we've seen that before. And we think about, okay, I'm going to describe the location of this point. If I describe the location of that point in the original coordinate system, that's not a centroidal coordinate system, then I can also describe it by the addition of this vector, which gives me the location of the centroid of that coordinate system, and then the location of that point with reference to the centroidal location. So either way you look at it, you have r is equal to r sub c plus this r prime. What is this r prime? That vector right there, r prime. It's the location position vector in the centroidal coordinate system. Or since we're really only interested in the y, you pick up that y is equal to y sub c plus y prime. Yeah, we substitute right in there. So you get the integral of the y sub c plus y prime squared dA, m over a. You pick up the integral of y sub c squared dA plus the integral of 2 y sub c y prime dA plus the integral of y prime squared dA. And then we just, all of that's multiplied by mass per unit area And what did we observe about the y sub c? That's constant, so it comes outside, so you're left with y sub c squared. That'll devolve to the distance squared between the two parallel axes. And then you'll have that m over a integral dA. That's just the mass. What about this term? Well, you pick out the 2y sub c, the integral y prime dA, and by definition, this is a centroidal, it goes to a centroid, and so there's equal area above and below that x prime axis. That's equal to 0. This is the integral y prime squared dA, y prime squared dA. When you bring in that m and a back into it, then we pick up the centroidal x-axis mass moment of inertia. So the non-centroidal mass moment of inertia with respect to the x-axis is equal to the equation that we just reestablished using the parallel axis theorem, d squared times m plus the centroidal mass moment. All right, press forward. Here's a problem. We have a pendulum. It consists of a 20 kilogram slender rod. So this part right here is where it's going to rotate around point O, and the slender rod is right here. What's the length of that rod? 0.45 meters. And 30 kilogram sphere. The sphere is centered right there. Its radius is 0.1 meter, and the mass is 30 kilograms. So they give us the mass of both of the rod and the sphere. Determine the mass moment of inertia of the pendulum about an axis perpendicular to the page. So it looks like a point. It looks like point O on our illustration. That's an axis. And passing through the point O. There you go. So what I want to do is I want to give you a second. How would you attack it? It's going to be a composite of a slender rod and a sphere. And you're going to have to say, where is the centroid of the slender rod? And where's the centroid of the sphere? And then use the parallel axis theorem to shift them up to center O. Make sense? Go ahead and get started. I'll pause and walk around and see how far you get. All right, I'll pick it up here. To calculate the mass moment of inertia, point O, you would do it for the rod and the sphere. For the rod, you can just use the 1/3, the mass of the rod, the length of the rod squared. And I think most people got that. And that came in at 1.35 kilogram meter squared. Thumbs up, just for the rod. And then for the sphere, you do it using the parallel axis theorem. So through the center, the centroid, they didn't call it anything, but through the centroid of the sphere, it's, what is that equation? 2/5 the mass of the sphere, the radius of the sphere squared. But then we have to add the distance that you move up. And the distance that we move up, that d squared, is 0.55 squared, right? Times the mass of the sphere, which is the 30 kilograms. So these are the 30 kilograms. And when you do that, the sum of them come in at 10.5 kilogram meter squared. So this was, what was this? 9.195. All right? Determine the mass moment of inertia of the thin plate about an axis perpendicular to the page and passing through the point O. So there's that point O. You can see now what you're leading into this dynamics where you're going to be swinging about that point O. And maybe there's some force and some moment of a force to create that acceleration. So this is hopefully understandable why you'd be interested in it. And the mass, the material has a mass per unit area of 20 kilograms per meter squared. Yeah, they consider it as a composite. One solid round plate, and then one the hole, and then you're going to subtract that contribution from the square hole out of it. Okay, now if we look at our textbook, do they give us for a circular disc, which is that plate, at the edge of it? Can you see, is there one equation? This would be on the back cover or the equation sheet I passed out last time. I'm going to pause, walk around, and I want you to show me that one as I walk around. You see what I'm asking? Yeah. Is there information right there that you can use? So hopefully everybody sees where in the textbook they give it to you for that z prime axis. So it's going to be 3/2 the mass times the r squared. This mass will be this 20 kilograms per meter squared times that area. What is that area? Isn't it pi r squared, which is 0.2, isn't this r right here, 0.2 squared? 0.2 meters squared. And what is this r? 0.2 meters. Are you going to square it? Okay, so that's, now you have to subtract the contribution from that square. All right, well, that square hole, I'm going to have to use the parallel axis theorem. I'll put it through this point. That's a centroid of my square. Do they give it to you anywhere on our sheet for the square? You just find it. What is the value for that thin square plate? Is it going to be the 1/12? The mass of the whole of the square plate times 0.2 squared plus 0.2 squared. I know A and B are the same in the equation, and you could simplify a little bit, but that'll work. All right. And then we use the mass of the plate. Let me should put an MP there and an MP for the mass, not of the plate, of the square. Mass of the square hole, times that distance. What is this distance that you have to move it for the parallel axis? 0.2. That's d squared, where d is 0.2 meters. True? All right, what is that mass of the square? That's that mass density, 20 kilograms per meter squared times 0.2 meters squared. And then once you compute both of these by summing them up, then you subtract it from the solid disk, and then you have the value. And the value comes in at 0.1135. You can round that off to 0.114 kilogram meter squared. Well, one last hard problem. A wheel is made of one large ring, so this outer ring is 100 pounds. And a small inner ring, that inner ring is 15 pounds. And each spoke has 20 pounds each. How many spokes do you see? Spoke 1, 2, 3, 4, 5, 6, 7. So 8 spokes, and they're 20 pounds each. Calculate the mass moment of inertia of the wheel about the point A right down here. So I know the wheel is sitting in an axis, and the it's rotating around that axis, but that axis moves. And if you think about it, I know this is dynamics when you get there, but at the instant in time when the wheel is moving, guess what? Point A is dead rest, is at dead rest. And for that instant, the whole system is revolving around point A. That's dynamics. Okay? But it's going to be important to get that mass moment of inertia for something like this around the point of contact, point A. So how would you solve this problem? Well, it's a composite, isn't it? The large ring, the small ring, and then a bunch of spokes. Well, take a look at the cover of the textbook. Do they give you any ring formulas? Sure. And so they give you the ring about the center O, the large ring. So let's just do the large ring first. So I of the large ring will be the m, the mass of the large ring, times the radius of the large ring squared. And then we have to use the parallel axis theorem to move it from point O, the origin, down to point A. And that will be the mass times the distance squared. This is funny. Doesn't look at that. They look like the same. They are. Mr squared, Mr squared. So this turns out to be, just for the large ring, 2mr squared. The mass of the large ring was 100, and the radius of the large ring is 4 foot. Okay, let's do it for the small inner ring. I is equal to the mass times that radius of the small inner ring squared plus the parallel axis theorem. That'll be the mass times this distance. D squared is not the same as that inner ring radius, is it? So if you want, maybe you put it like this. That inner ring was 15 pounds, and it had a radius of 1 foot squared, but we have to move it 4 foot squared. I'm leaving the units off, just showing you how the equations work out. Now you have a choice. If you do each of these spokes, you would treat it as a slender rod, right? And I would go and say, okay, well, for rod 1, where is its center? The center of mass, the centroid of that rod 1 is right there. And I'm going to have to figure out how to move it down to this point, and I'm going to need that distance D. You can definitely do it this way. If you do it that way, you're going to get a triangle, and you probably want to use this angle right here is probably fairly easy to get right there, that angle, right? Because for this one, for rod 8, that triangle, oh, that's a right triangle. I like that. It's 90 degrees. But for rod 1, it's not 90 degrees for that angle, and we're going to use a law of cosine. It's a good little review. You could do it that way. All right, and you'll have to do the same thing for rod 7, like that. And that angle opposite the distance you really want is pretty easy to compute. It's 45. For rod 8, it's 90. For rod 1, it's 90 plus 45, 135, 135 degrees. And then if you actually do it for rod 1 and do it for rod 3, they have the same distance. They move it. The rod 7, the rod 5, they have the same distance. They move. And the rod 8, the rod 4, they have the same distance. All right. And then rod 2 is unique, just moves it down. And rod 6 is unique, moves it down. Okay? You can definitely do that. Little bookkeeping, it'll work. There's another way of doing it. What you can do is say, I don't really have 8 rods, I have 4 rods. Then I take off the section in the middle. Let me see if I can draw that. So I would say I have 1, 2, 3, 4 rods. And then I'm going to subtract 1, 2, 3, 4 rods that are much smaller radius. Because I know it's easy that the center of mass for each of those longer rods are all at 0.0. I avoid this calculation of this distance. Both ways will give you exact same answer that's correct. Okay, so what is the answer for this problem? And then we'll press forward. The mass moment of inertia about point A is 7,135. This is units of mass as pound and distance foot squared. Now it's a little long problem. It's a little tedious. You have some choices which way I go. Okay? All right. With that, I'm done with the... yes?
Sorry, just if you're going to do that second way, how much would each both weigh? 40 pounds?
Oh, no. Yeah, you have to figure out what is the dense... So we have 40 pounds in 6 foot of actual. And so now you have that ratio. Now I don't have 6 foot, I have 8 foot, right? So then I'd multiply by 8 foot, and so each long rod would have, more than 40 pounds. But then guess what I'm going to do is I'm going to subtract off that 2 foot, which is whatever. This is what, 4/3 of 40, and then I'm going to subtract off 1/3 of 40 for the 2 foot here and 2 foot there and 2 foot, Yep.
So it's just 40.
Yeah, you're back to mass of 40 actual. But when you compute it, you do it for the whole rod, and then you do it for this red rod section. Right. Make sense? Okay. All right. So we're finished with this chapter on moments of inertia. We covered the area moments, and we ended with the mass moment of inertia. Hopefully that's a good lead into dynamics. With that, what I'd like to do is talk about the exam and what do we do on Wednesday and help in preparation for the exam on Friday.